All right, y'all. Today we're going to be talking about what we call instantaneous rate of change versus average rate of change. Okay. Or for short, IROC and AROC. You're going to hear me say that all the time because this is really kind of this important theme of derivatives of relating these two together. So AROC stands for average rate of change. All right. And my AROC is if I had a nice little function. Look at that beautiful, nice little function. And I picked two different points. So let's say this point here and this point here. I could find the average rate of change between those 2 points, which would give me a slope, because a rate of change is a slope. It's some rate that's changing over time. So some value y changing over some value x, or time, or something like that. Okay. We also say that this is delta y over delta x. It is also, as we talked about last class, the secant line. Okay, so the secant line is that rate of change over 2 points. It's that average rate of change. Okay, it's an average because it's over time. It's not a specific time. Okay, versus what we call IROC, our instantaneous rate of change. So, similar function. If I picked a very specific point, so let's say this same point here, I could find the slope at that specific point, okay? And we call that the tangent line. And that slope, not delta, is our derivative. Okay, so secant is kind of what you've been doing before in algebra and in physics. It's that average rate of change over some time interval. What we're advancing it to in calculus is that instantaneous rate of change, that IROC, that tangent line, finding that derivative. So let's dive into AROC a little more. So average rate of change is the amount of change over our length of interval. So essentially, delta y over delta x, or rise over run, or y2 minus y1 over x2 minus x1, or, as you're going to see it referred to this year, f of b minus f of a over b minus a. So these are all the same thing. They're all that average rate of change. These are just kind of advancing it through the years of math. And in calculus, we're going to refer to it as the function value at b, so that y value at b, minus the y value at a over the change between b and a. Okay, so it's that same thing. It's that change in y over change in x. This is just how you're going to see the equation referred to in calculus. All right, now let's look at a quick example. 1, 2, 3, 4. 1, 2, 3. Okay, so let's say we have this function, and I want to find that average rate of change on the interval a 2 to 3. Well, 2 and 3 are my a and b. So I'm doing f of b minus f of a over b minus a. So I would do f of B, f of 3 minus f of 2 all over 3 minus 2, which would be equal to my y value at 3 is 0, minus my y value at 2 is 4, over x value 3 minus 2, which is equal to negative 4 over 1, which is equal to negative 4. And what we just got, this is our average rate of change. So if I drew that secant line, okay, the slope of that secant line would be negative 4. Okay, so that's average rate of change. Average rate of change should be very similar. Okay, the way that you know it's average rate of change is that I give you an interval. So anytime I'm asking you to find change over an interval, it has to be AROC. Okay, now let's dive a little deeper into IROC. Okay, IROC is the rate of change at a moment in time. Okay, and we also refer to it as the slope of the tangent line. Okay, so big difference already between AROC and IROC. AROC is over an interval. IROC is at a specific point in time. Okay, to find IROC, okay, this is kind of our process. You've actually been finding IROC before. Now we're just going to put it into more of a step-by-step process. So the first thing I need to find is my coordinate point. So I need an x comma y point. You're probably going to be given it, or you might just be given an x value. And sometimes you may need to plug one in to get the other. Just depends. Okay, so once I have my coordinate point, I'm going to take the derivative. So my derivative is an equation. So remember, we talked about this all last class. My derivative is an equation. So you should have some f of x or some y equals or some h of x or g of x. We're going to take the derivative of that equation. Okay, so the derivative is an equation for the slope of the tangent line. And we also refer to our derivative as a slope generator. Okay, because it generates slopes at all points on a function, right? Then we're going to find the slope. How do we find the slope? By plugging x into f prime of x. Okay, so we just take that x value and we plug it into our derivative. Okay, that's how I find instantaneous rate of change. Instantaneous rate of change is the slope of the tangent line. It is the slope. Okay, so average rate of change is a slope, but it's that rate of change, that slope over an interval. Instantaneous rate of change is that slope at a specific moment of time at one time value. So it's really, really clear. The questions aren't always going to say find AROC or find IROC. They're just going to say find the rate of change from 2 to 3, or they'll say find the rate of change at 3. Okay, so they're going to tell you either a point in time or an interval, and you have to know interval means average, point means instantaneous. Okay, now one thing that you might have to do, it's just if needed, you're not going to always have to do it. You might also have to find the tangent line equation. Okay. Now, as a reminder, that is y minus y1 is equal to mx minus x1. Okay, and we use that to write an equation in our point slope form. And remember, our point is at x1 comma y1. Our slope is m. So that's just if needed. Sometimes it asks for it, sometimes it doesn't. Okay, let's actually look at an example. All right, if a billiard ball is dropped from a height of 100 feet, its height s at time t is given by the position function s is equal to negative 16t squared plus 100, where s is measured in feet and t is measured in seconds. So first thing I just want to point out, calculus does this weird thing where it uses s for distance instead of, d. Don't ask me why, but it's just really, really common. So when you see s, just don't get super distracted by it. Okay, so first we want to find the average velocity over the interval 1 to 2. Okay, so I want see the word average, so that should be easy. I know I'm doing AROC. Okay, because I'm doing AROC, it is f of b minus f of a over b minus a. I look at my interval. My interval is an a to b interval. So I'm finding, let's change it to s. So s of 2 minus s of 1 over 2 minus 1. So s of 2, plug it into your equation. Okay, for time's sake, I'm just going to give you these values. So we would get 36 minus 84 over 1, which 36 minus 84 equals negative 48 over 1. So we get negative 48. And this is an actual velocity. So looking at our feet and seconds. So 48 feet per second. Okay, one of the big things in calculus is when we do work with real values, with real actual units, you have to include units. Okay, so negative 48 feet per second. Okay, and remember, that is an average. That is the velocity over the time interval 1 to 2. Okay, so B, we want to find the velocity of the ball at t equals 1 second. Okay, so at 1 second, that means IROC, velocity at a point. Okay, so if I'm finding velocity at a specific point, then now I'm finding my derivative. So I want to find s prime. I'm going to say of t, even though it just says s prime of t because it's s of t. So I'm taking my derivative. So the derivative of negative 16t squared is negative 36t. And then 100 just goes away. So that is my derivative. And then I want to find that value at 1. So negative 36 times 1. Wait, 36. I'm a crazy person. 32. It's late, y'all. So negative 32 times 1, which just gives us negative 32. And this is still a velocity. So negative 32 feet per second. So just to kind of put this in perspective, like what does this mean, Mr. Arbone? What are these values telling us? So what this is saying is that my billiard ball being dropped over the interval 1 to 2, its average speed over that interval is 48 feet per second. Okay. Part B is saying that its speed at exactly 1 second is negative 32 feet per second. So that makes sense, right? If it's falling, it should start to fall faster and faster over that time interval. So at the beginning of the time interval, it's probably falling not as fast as negative 48, but towards the end of the interval, so like if I found the slope at 2, we should be getting something bigger than negative 32, which if I plugged in 2, negative 32 times 2 is 64. So you would get something much larger than 2. Okay. So that's what these mean. I just kind of want to try and put these in perspective so you're understanding what are we actually finding? What does this represent? Okay. I'm going to do number 2 with y'all, and then I think you can find 3 on your own. Okay. So at time t equals 0, a diver jumps from a platform diving board that is 32 feet above the water. The position of the diver is given by S of t is equal to negative 16t squared plus 16t plus 32, where S is measured in feet and t is measured in seconds. So A, when does the diver hit the water? All right, now this might seem like a trick question. Okay, I'm asking for a when. What does when mean? When means a time, okay? So are we finding AROC or IROC? No. So don't just get tricked by these real world situations. They're like, oh, I'm just finding one or the other. Always read the question, find what it's asking you to find. So I want to know time. When do I want to know time? When I hit the water. So what's happening when I hit the water? Height would be 0. So I want to know t when s is equal to 0. So let's set that equation equal to 0. So 0 is equal to negative 16t squared plus 16t. Ooh, go away. Purple. Equals 0. So, like Mr. Bone, I don't know what I'm doing. Well, harken back to algebra 2. We're just going to be factoring. Okay? So 0 is equal to, I can take a negative 16 out of everything. That gives me t squared minus 2t, not minus 2t, minus 1t, minus 2. So that would factor into t minus 2 and t plus 1, which gives us t is equal to 2 and negative 1. Now, only one of these seems actually makes sense in the concept of our problem. So that would be 2, because I can't go backwards in time with my diver. So t equals 2 would be when the diver hits the water. All right. B, what is the diver's average velocity while in the air? Okay, well, they use the word average. So what are we finding? AROC. And while in the air, so that's an interval. My interval would be from 0, because that's when I start, to the time we hit the water, so 2. So I'm finding S of 2 minus S of 0 over 2 minus 0. So we should get 0 for S of 2, 32 for S of 0 divided by 2, which would equal negative 16. And then, oh, sorry, I forgot a time. This is still seconds. And this would be feet per second. Okay, so remember, this is an average. So on average, while my diver's in the air, he's moving negative 16 feet per second. Okay. So now, let's look at C. What is the diver's velocity at impact? Okay, so I want to find velocity at impact. That's at a point in time. Okay, so this is IROC. And at impact, what time do I hit the water? At time t equals 2. So to find IROC, I need to find my derivative. So I need to find my S prime. Okay, so S prime of t is equal to negative 16t squared becomes negative 32t plus 16t becomes just 16. And then plus 32 becomes just 0. So I have what my S prime would be equal to, which means S prime of 2 is equal to negative 32 times 2 plus 16, which is negative 64 plus 16, which gives us negative 48 feet per second. So we're still working with a velocity. Okay, what is the diver's initial velocity? So I just found my derivative, which is my IROC. So S prime of t equals negative 32t plus 16. So initial would mean t equals 0. So I set S prime of t sorry, not s prime of t, s prime of 0, so I can find that initial velocity. Negative 32 times 0 plus 16, which gives us 16 feet per second. Okay. And then last but not least on this one, when is the diver's velocity 0? Okay. So now once again, I'm asking a when. So time equals what? Velocity 0. So velocity equals 0. And we kind of talked about this already, y'all. Okay. But I want you to notice S prime is really just my velocity equation. Okay. So we're going to talk about this more, but our derivatives actually represent real equations in the real world. So I want you to kind of be connecting it to some things you've kind of done before in physics. This would be our particle motion. Okay, if those of you who have taken physics before, just to kind of connect it to stuff you've done, stuff you've seen. Okay, so when is diver's velocity 0? So I'm going to take my velocity or my s prime of t equation and set that equal to 0. So 0 is equal to negative 32 t plus 16. Solve that out. We get 32t is equal to 16. Divide by 32, divide by 32. And we get t is equal to 1/2 second. So a half second up into the air is when our velocity would be equal to 0. All right, y'all. I'm going to let y'all do 3 on your own real quick. All right, y'all. So average rate of change, a to b, f of 2 minus f of negative 3, 2 minus negative 3. Remember that minus a negative becomes a positive. F of 2 is 9. F of negative 3 is negative 126. So that negative and negative also becomes a positive. Simplify that out and you get 27. Okay. Instantaneous rate of change, we find the derivative. I plug my x value into the derivative and evaluate all the way out. We get 107. Now, one thing I want you to notice about 3 that's different from 1 and 2, I didn't have any units. That's because this was just a function I told you to find AROC and IROC. I didn't give you any units, any real world situation to work with. So if it's a real world situation, make sure you're looking for units. If it's just a regular normal old situation, you don't got to worry about units. Okay. So the last thing we're going to talk about today, y'all, and this should be really, really quick, is differentiability and continuity. Okay. So differentiability, I said this real briefly last class, but differentiability means I can take the derivative. Continuity, we know that it means the function is continuous. Okay. So some things about the two, if a function is differentiable at x equals c, then it is continuous at x equals c. So what that means is that if I can take a derivative, then my function has to be continuous, which is, if you think about that, that makes sense, because to be able to find a slope at a point, my point's got to be there, my limit's got to be there, the whole function has to be working. Okay. But it is possible for a function to be continuous and not be differentiable. Okay. Now, the reason for this, okay, is these two situations, a graph with a smooth curve versus a graph with a sharp turn. So I want you to think about, what is the derivative? Well, the derivative is the slope. Okay. So on my smooth curve, if I'm finding these slopes, so let's see, slope at here is, a pretty negative number. Slope here is going to be a little bit of a less negative number. Slope here, a little bit of a less negative number. And then right here at 2, it's going to become 0. And then it's slowly going to start increasing positively. Okay, so we kind of go gradually from negative slopes to 0 to positive slopes. Okay, the key word here is gradual. I can find values of the slope the whole way through the whole way. Okay, over here on my sharp point, well, over here, okay, my slope is always the same negative value all the way up until here. And then on the right side, my slopes are the same positive value. So let's just say, which we don't have to just say, we can say, this is a slope of -1. This is a slope at +1. So does it make sense for me to go right here at, let's say, like 1.99999 for my slope to be -1, then at 2 for my slope to be 0, and then at 2.00001 for my slope to be 1? No, because if I was to actually try and graph that derivative function, okay, it'd be this big old mess with negative slopes, positive slopes, like this, -1 and +1. Okay, so what's going on here? I would have a jump discontinuity. Okay, so the key thing that I want you to get at, okay, is that graphs with smooth curves, smooth points, continuous functions, I can take my derivative. I can take my derivative specifically at those smooth curves, kind of those rounding out points. If I have these sharp turns, okay, so this sharp point like on an absolute value function, you could have like a cusp is another kind of sharp turn, okay, something like that, then I can't find my derivative there because of that sharp drastic change in slope. Okay, it doesn't make sense if I was to try and graph it. Okay, so for 4, 5, 6, and 7, what we're going to do is we are going to graph the function f prime from the function of f. So 4, 5, 6, and 7 are all f. We're going to try and graph f prime. Remember, f prime represents the slope at any point along f. So looking at 4, okay, the slope along every single point in this line is +1. Okay, so if I wanted to graph f prime, I'd graph a nice straight line with a constant value of 1. Okay, to help make this make a little more sense, the function of f would be -4, so x minus 4. So what would the derivative of that be? Well, that would be just 1. So do these graphs match up with our functions? They should. Okay, so remember, f prime is a derivative. The derivative is a function that represents the slope at any point on f of x. Okay, so it should represent those values of the slope. So let's look at 5. 5, here's my f. Okay, what's my slope at any point along this line 4? Well, it'd just be a flat slope, which the flat slope is just a slope of 0. Okay, so if my slope is 0 everywhere, then my f prime would just be a line at 0. Okay, to put it in perspective, f of x would equal 4, which means f prime of x would equal 0, to kind of match up those graphs to equations. Okay, I'm going to let y'all try and do 6 and 7. So pause the video, try and do 6 and 7, and then start the video again and I'll explain them. All right, y'all, so hopefully this is what you got for f and f prime. Okay, so on 6, for my parabola, here to the left of my parabola, so I'm going to split it down the middle, are my, here to the left are my negative slopes. And up here at like 1 would be a really negative slope. Then at 2, my slope would be a little less negative. Then at 3, it would be a little less negative. Until right here at 4, my slope would be 0. So I cross right here with f prime. And then all of a sudden on the other side of my parabola, my slopes become positive. So that's why my f prime graph would just be a linear line, which from what we know of our functions, if f of x was equal to x squared, f prime of x, wrong color, would equal 2x. Okay, derivative of a parabola should be a linear line, so those equations should match up. All right. On 7, this one's kind of that what we talked about, that sharp point. So here to the left of my absolute value, my slope is -1 consistently. Here to the right of my absolute value, my slope is +1 consistently. But right there at 4, I can't find my derivative. I can't find my slope because of that drastic change from -1 to 1. That doesn't make any sense. Kind of think about it like your two left and right side limits not being equal to each other. So because of that, I can't find a slope value at 4. All right, y'all. That concludes IROC and AROC and continuity and differentiability.